All right, let's look at theorem 5.11, the orthogonal projection formula. This tells you basically how to get the projection of any old vector y onto a subspace W. But notice that this only works if you have an orthogonal basis of W. Now, this formula, it's the same thing we did in that example 1 here. Of course, E1 and E2 is an orthogonal basis of the column space of E1 and E2. So it worked there, and it works in general. And one thing to notice here is that if you have an orthonormal basis of W, meaning unit vectors, then all of these denominators are actually 1, which makes the formula simpler. You could just ignore the denominators and just calculate the top part. So let's prove this. This proof is going to be not too bad. So we're assuming all this stuff, assuming you have an orthogonal basis of W and Y is in our R. Well, we know that projections exist and are unique. That was the first theorem in the section. And we know it's in W. We're assuming we have a basis of W, so we can write it as a linear combination of those basis vectors. Because U1 through UC is a basis of W, there exists a unique X1 through XC way to write the projection, which we should call Y hat, as a linear combination of the basis vectors. Now, we want to show that each of these coordinates, like x1 through xc, is essentially the coordinate vector of y hat. We want to show that each of these coordinates satisfies this formula we're giving here. So that's our goal. Now, to do that, a trick when you have an orthogonal list of vectors is to take some dot products that you know will come out to be 0. So what I mean by that is see what happens if you take one of these ui basis vectors where I is something between 1 and c, and do the dot product of that with this projection. But we know we can write y hat as this linear combination. And then we have a distributive rule for dot products. So we can distribute that in. Now, most of these are going to be 0. Like if I is not equal to 1, then ui is orthogonal to u1, so their dot product will be 0. So this is going to be x1 times 0. All of these are going to be 0 except for ui.ui because it is an orthogonal list. And what is ui.ui? Well, if it's orthonormal, it would be 1. Otherwise, we don't know. Whatever it is, it's the length of ui squared. So, in other words, we have ui dotted with the projection of y onto w is just equal to this part because everything else must be 0. So if you just divide both sides of this equation, everything here is just numbers. If you divide everything by ui dot ui, that gives you the formula we want. Well, sort of. What we're trying to show is that if we do ui dot y in the top over ui dot ui, you get xi. But this is not quite there yet. We just need to show that these are the same. That ui dot y is the same as ui dot y hat. And to see that, we're going to use the fact that ui dot y, well, let's look at the picture over here. We can write y as the projection y hat plus y minus y hat, right? And then you can distribute the ui into that. And what do we know about ui dot producted with y minus y hat? Well, y hat is the unique vector that makes it. So this orthogonal part, y minus y hat, is orthogonal to everything in W. So yeah, ui dot y is the same as ui dot y hat plus 0. So those are equal. And that means that you can replace this y hat in this formula we just found with y, and you get the same thing. And so yeah, that works in general. Let's do an example of applying this formula. Here with example 5 and example 6 maybe. So in this case, W is the span of 1, 1, 1. And the vector 1, 1, 1 is actually an orthogonal basis of W. Because this u1 vector is orthogonal to every other vector in the list. There are no other vectors in the list, so it's vacuously orthogonal. Let's find the nearest point in W to y and find the distance from y to that point. So let's use the theorem. So the nearest point in W to y, looking at the best approximation theorem, if this is y out here, the nearest point in W to y is going to be the projection, because that's the point where the distance from y to W is the shortest. And we're going to do y dot 1, 1, 1 divided by 1, 1, 1 dotted with itself, and multiply that by 1, 1, 1. So that's just going to be 15 divided by 3 is 5. And 5 times the vector 1, 1, 1 is 5, 5, 5. And maybe that seems reasonable. Like that is definitely in the span of 1, 1, 1. And we got the 5 exactly equal to the 5, and the 4 is pretty close to 5, and 6 is pretty close to 5 too. So that seems reasonable that that would be the nearest point. But let's actually find the distance from y to that point. That's going to be the magnitude of y minus y hat. Y minus y hat will be 4 minus 5 is negative 1. 5 minus 5 is 0, 6 minus 5 is 1. And the definition of length, or magnitude, whatever, is, we'll do negative 1 squared plus 0 squared plus 1 squared, which gives you the square root of 2. And if you wanted to be sure that it was really the nearest one, you could try something a little different. You could try like the distance from 4, 4, 4 to 4, 5, 6. 4, 4, 4 is just a nearby point on the span of 1, 1, 1. That'll come out to be the square root of 5, which is bigger than the square root of 2. Or if you go a little bit further in the span in the other direction, that's also going to be a distance the square root of 5 away. So yeah, so this is the shortest possible distance from 4, 5, 6 to any point in the span of 1, 1, 1. Okay, let's look at example 6. Here we have a block that weighs 4 pounds, and we got the pictures set up already, so you don't have to draw the free body diagram yourself. We're setting up the coordinate system, so when x2 is a negative number, it means that's downward. And the block is on a slope, an inclined plane, with slope 1 over root 3. So a unit vector that is parallel to that slope is this u right here. And notice that the magnitude of this is 1, so this is a unit vector. And we want to find the components of the weight of the block that are parallel to the slope. Notice the slope is the span of u. And also the part of the weight that is like perpendicular to the slope. These are things you might need to know if you're doing physics or engineering. You want to know how much force of friction is being applied to it and how hard the surface itself is pushing back up. Anyways, let's do this the linear algebra way. You've probably done this in physics or calculus class by like realizing, oh, this is 1 over root 3. This is going to be an angle of 30 degrees, and then doing sine and cosine of 30 degrees. That's fine too, but let's do it the linear algebra way here. So the y hat vector here, this is in the span of u. I mean, it's drawn sideways, but of course, y hat, you could draw a copy of it starting at the origin or something, and it's parallel to u. And the component that is perpendicular is going to be y minus that y hat. And these should add up. Y hat plus y minus y hat should add up to y. So yeah, let's use the formula for y hat. In this case, u dot u is 1, so we have like the simplified version of this. We can just do y dot u as the scalar and multiply that by u. And y dot u here, we're going to do 0 times root 3 over 2. That's going to be 0 minus 4 times 1/2. So that's going to end up being negative 2 times this u, which will be negative root 3 and negative 1. So that's our y hat. That's our component that's parallel to the inclined plane. Has to do with how much friction the block is making, etc. Let's get the perpendicular component, or the normal force, you might call it. So you get that by subtracting 0, negative 4, minus negative root 3, negative 1, which comes out to be the square root of 3, and then negative 3. Now, we don't just want to know like these as vectors. If you're doing physics, you want to know like how much force is there parallel to the slope, how much force is there with friction, and how much is the normal force. So we need to get the lengths of these vectors, the magnitudes. So let's do that. The length of y hat is going to be the square root of negative root 3 squared plus negative 1 squared, which comes out to be 2. The length of this perpendicular component will be the square root of 3 squared plus negative 3 squared is the square root of 12, also known as 2 root 3. And you might be noticing that these add up to more than 4. But that's what happens when you add vectors. We could check that they are actually perpendicular using the Pythagorean theorem. If you do 2 squared plus 2 root 3 squared, do we get 4 squared? The length of y squared, the hypotenuse? Yes. Okay, so yeah, they do indeed make a right triangle. Just checking that using the Pythagorean theorem. And we're good. In the next video, we'll look at least squares solutions, which is thinking about what about when W is the column space of some matrix A? How do you find the point in the column space that is closest to making A x hat equal to Y? But we'll see that in the next video. So I will see you then.